Okay. Um, Hello, everyone. Thank you for joining Capstone Project presentations of WaterSoftHack program. So we have four groups today. They present their Capstone uh, research work. And the first group is water quality group. The second group is remote sensing group. The third one, hydrobac. And the last group is drought and risk group. So we go with the first group. So water quality group, if you guys could share your presentation. All of you, you have 10 minutes to present. And we have 5 minutes for Q&A. So prepare for Q&A. So to address question from us and also audience. Hopefully we finish within 5 minutes. Okay, you guys start.
All right, so good morning, everyone. My name is Moses Chwanka, and we are the Water Quality Group. We are looking at comparing multiple machine learning models for sediment forecasting. We are with Ariana, Garina, Emmanuel, Alex, and our advisor is Professor Videla. Next slide. So suspended sediment is a fundamental component of the river system. It plays a very critical but yet complex role in the ecological health and the geomorphological processes, and also looking at the water resources infrastructure. While it's very important for habitat formation and nutrient transport, its excessive concentration can pose significant challenges, especially after heavy storms. It leads to water treatment disruptions, ecological degradation, infrastructure impairments, because we know that streams have multiple dams and such infrastructures can be impaired. Our core problem lies in our limitedness in trying to forecast these extreme events, which are of a major challenge. Please go ahead, slide. So the problem statement is one thing that we can talk about is there is no continuous data, especially here in the US. It's very limited, and there are also challenges to do with lab analysis and sensor calibrations. This makes most of the traditional field methods incapable of capturing this suspended sediment, especially in extreme events, because one, as suspended sediment are highly affected by natural processes and, uh, and human activities. So these field methods are not able to capture that complex and dynamic interaction. But the good thing is that we have stability data, which is readily available and can be used as a proxy. So that's why we decided to use stability data in trying to answer our research questions. Can we use machine learning to forecast these extreme events, especially in the Sacramento River? And which of these models can be appropriate in future forecasts to prevent the significant challenges that can be caused by the extreme events of suspended sediment. Next slide. So we did a survey, the literature review, and we're able to find out that most of the methods that are used in the field are conventional statistical methods like sediment rating curves and multiple linear regressions, which can't capture the nonlinear component of this suspended sediment because it's highly variable, as said earlier. A few machine learning models like the FFN and the multi-layer perceptron, which are not very also appropriate, and some hybrid models like the wavelength. But in our literature review, we didn't really get to see much of the work done using the LSTM or the transformer model, which became our major focus point in this particular work we are doing. Ariana?
So our study area is a very large basin in the Sacramento River. This is in Northern California, and there are over 300 dams in that watershed. Dams can be impacted by sediment when they fill with sediment and the capacity is reduced, and which can increase the risk for dam failure. So that's why we are studying this phenomenon. And the data we found is water discharge, and also suspended sediment concentration at the daily scale. The USGS gauge we were looking at, which is that red point in the map, also collected turbidity at a 15-minute interval. And so there was a period of overlap that spanned about 14 years where all data was available. So that's what we focused on. And the general method we used, we used the same hyperparameter values for most of the models, MLP, LSTM, and Transformer. And then we trained those models with the optimized hyperparameters. And we used a sequence length. Initially, we used a sequence length of 1 day based on the time of concentration, which is a physical parameter that represents how long it takes water to flow from the farthest point from the outlet to the outlet. But that 1 day sequence length produced really unrealistic results. So for this presentation, we are comparing results using a 7-day sequence length and a 14-day sequence length to look at the differences. And so moving now to the results, we start with the multi-layer perceptron, which is the simplest neural network. We're using this as a benchmark because it's already used in the field. And a 7-day sequence length produced very bad results. Essentially, we think it's the look back window was not long enough for the model to understand what was going on. But using a sequence length of 14 days, the model was actually able to capture the timing of peaks pretty well, even though it wasn't able to capture sort of low and base flow levels very well. And so selecting an appropriate sequence length is key.
Yeah, so similar to the multi-layer perceptron, 2 LSTM iterations, one with a sequence length of 7 and the other with a length of 14. And this was kind of intended to test the sort of different potential physical processes that govern sediment transport. We found that longer sequence lengths exhibited better performance than the shorter lengths when holding the other parameters constant. This suggests that the 7-day sequence length is likely truncating some kind of meaningful lagged information that is better captured by the 14-day sequence length. And the physical processes that control sediment transport, such as storm-driven sediment pulses and longer basin travel times, could take longer than 7 days, which kind of could explain the decreased performance in that sense. But across both models, there's kind of systemic underestimation of the observed data, except during extreme events and high peaks where there is some overshooting in the simulation. And this could be due to, a lower quantity of extreme training data, which is an exhibited and realized problem in the literature.
Okay, for transformer model, we also use the same range of hyperparameters to pick from with Aptuna model, with Aptuna optimization. And then we use the same sequence length of 7 days and 14 days. And the results are somewhat similar to the other models. So with the longer sequence length of 14 days, we have a model that captures our suspended sediment concentration better, but both of them heavily underestimate the peak events. So both type of models, they really struggle with those outliers and the peak events, and they underestimate the highest peaks. There might be different reasons that cause that. For one, it can be that our suspended sediment concentration signal is pretty noisy because this is a dynamic variable that has an effect from different physical processes, and our input parameters are not capturing all of them. So maybe increasing and adding some other predictive variables might help with the model performance. And also playing with the different sequence length might help. So trying longer sequence length maybe increase the performance of the model. Next slide, yeah. Bali, you're muted.
All right, so the GRE model used 60 days of ideological input along with 17 engineered features such as precipitation memory, discharge, and event response dynamics. This is probably to capture the complex watershed behavior. Using the NSE, the model shows strong predictive performance and generalization to unseen data. Interestingly, the NSC scores improved from the training set to the test phase, indicating that the model learns the robust ideological patterns rather than overfitting the dataset. Just like other model, the main limitation is performance during high flow events. Then this is precisely when sediment management is most important. Now, to address this, probably recommend implementing a weighted loss function to prioritize peak SSC predictions and incorporating hysteresis features to better capture sediment flow lag effects. Next slide.
All right, to conclude our project, we compared different model performance, and we can say that 14-day sequence length was capturing suspended sediment concentration better for MLP model and LSTM model and the transformer model. So longer sequence length actually plays better with both normal flow and extreme flow. And GRU model performed well on unseen data, but again had some struggles with the high flow events. So this was kind of the common problem for our models. They really struggled capturing high flow events, rather underestimating it like transformer and MLP, or overestimating like LSTM. Nonetheless, those models can be used to predict suspended sediment concentration. It's just a matter of time and data preparation, and adding more variables might help with the model prediction, as well as changing the estimated sequence length time. Yeah, thank you.
Great. Great presentation, guys. Thank you for your hard work on this. Okay, any question from audience and from the judges? You can also enter your question in the chat.
Hi, can I ask a question, Vidya?
Yes.
So, I was curious, like, how did you evaluate the difference between, like, the peak prediction and like a non-peak prediction and outlier events, right? So the peaks tend to grow exponentially higher and then come down. Like, did you adjust for any of those things?
Well, first, for our first idea was actually to look more closely into the peak events. So we actually did a classification on all our data using the percentile technique. So everything that is lower than 10% of the values of suspended sediment concentration would consider like drought events, actually even compared with the discharge, so discharge and suspended sediment. So less than 10% will be considered drought, and more than 90% will be considered at peak. But then we figured that we don't really have much time to really train well our model on the flow, so it predict only peak events. So we decided to not go that deep into this road, and we just use the entire data set after we fill the gaps, and work with NAs to look just how the model overall predicts both normal values and extreme values.
Did you like also try predicting like how far into the future you can predict accurately?
I guess that will be connected to the sequence length as well, right? So we tried only 7 and 14 for the sake of the time, but actually I think we tried 360 just out of curiosity, and it performed even better. Because when we were trying to understand what sequence length gonna be best for our model, we tried, as Ari said, this complicated model with ArcGIS, and it didn't really work well because it provided a value of 1 day. But we also tried fast Fourier transform to get some sequence length from there, and this one provided 361 days. So that's why for out of the curiosity, we tried this one too, and at least for transformer model, it worked better than even 14. So yeah, forecasting on different length will have the effect on the model, and that is something that we might work on future.
So maybe the 361 worked because it's very close to a year, and there might be like some annual cycles.
Yeah,
Yeah,
that's what we thought.
Okay, sounds good. Thank you.
Great. Any other question you guys may have? Okay, I have a quick question from your group. So you guys consider 7 and 14 for the sequence length. Could you tell me, how this could differentiate the performance of the model, and how you see the improvement when you change that values when you put your model, different model for run, how that impacted your modeling performance, how much it improved your accuracy when you incorporated that variables in the model.
Yeah. So we kind of thought that given the kind of very large kind of stream length and area of the watershed, that certain kind of event-based sediment transport processes would, either take longer or less time. And we kind of envisioned that because of the higher performance of that longer sequence length, there could just be kind of a long sort of transit time within the watershed that requires a bigger kind of context window to get at those kind of lagged dependencies that we saw. But yeah, we kind of wanted to do like we thought that a week, 2 weeks could be a good contrast between that kind of transit time question.
We
Right.
also figured that, for example, for transformer model, the NSE changed from 0.7 to 0.68. Not a big change, but still a little bit of a difference between 14 days and 17. So 14 days had a slightly higher NSE and lower WIP values.
Okay.
So that accounts for a better performance. And we also have all the values in the paper.
Okay, great.
I just don't really remember them by heart.
So yes.
I was just going to very briefly add for MLP, the difference between 7 and 14 was very large. And at a 1 day, the model also was not like responding very much at all to time. Like the prediction wasn't changing with time. So I think MLP specifically needs a certain length, a certain long enough look back window to understand the time series.
Great. So 6 to 7% is really significant, particularly if your model, imagine if it is unsatisfactory. For example, if you get less than 0.55 for your Nash coefficient, and then if you adjust your sequence length, and if it goes 6 to 7% up, then it can jump from unsatisfactory to satisfactory category. So you guys can imagine that one as well. So I have a final question from your team. All of you can chime in. This is for us as a WaterSoftHack team for the future, how we can serve our community better. So we wonder what type of challenge you guys encounter during conducting this research. I understand that 1 week is just short, but that's the nature of this program funded by UNICEF. But we would like to hear your kind of challenges you had during the project and picking up the study area and the data models. We'd love to hear about your challenges if you have any comment.
So I think for me, one major thing that the group really struggled with was in terms of aligning how to pursue the research, in terms of if it's going to be a process-based research or probably a methodology-based research, because as scientists, we always want to like make sure we cross all the T's and, but then given a time frame, we're not able to like do too much like focus-based. For example, in a study area, it's a highly regulated river, but then we're not able to like capture in cases where you had dam pulses, pulse release from the dams, and how that would impact the data we got from the sensor. So those are things we would probably do in the future, but then it's just a time frame. Yeah.
Yes. Thank you. Any other
Yeah.
comment?
Yeah, no, I think I agree with that. I think the kind of application of the neural networks and the methods, went really smoothly based on the training in the first week. But yeah, I just think the hardest part was, coming up with a research question, deciding how we were going to equally address it with different models and things. But of course, that's also probably the hardest part of research generally.
I would second on that, and also maybe this is not very valuable input, but we had a little bit of a struggle when we were trying to work on our models. The code that was provided for us previous week was just great, and we really appreciate that we had this like draft version that we can start from, so we're not doing ours from scratch. But sometimes it was a little bit confusing. For example, maybe we missed it, but some pieces like after you get data from Aptuna model, how to rerun the final run of your model, how to grab the parameters that Aptuna suggests to you and then run your model back. I mean, it's not something that is very hard to figure out, but it's just we struggle with that a little bit, and then we found a way, and then I guess it was easier from this point. So yeah, maybe this tiny little detail would help to proceed even faster.
Yes, great. So those feedbacks are helpful for us to update the package
Very
so
true.
that we can make it like more user-friendly for people to use. So any other feedback you guys may have?
Time.
Yes, Moses.
No, I think well, it might not be related to the data, but maybe the time, just the time, much as it's a 1 week's project. I think this was also proposed last year. If we could maybe embark on it like on the last day of the first week, we can get to do this maybe from the morning session, not only the afternoon. It would really help.
Okay, great. Okay, any other feedback you guys may have? That's wonderful. Okay, so any other question you have from this group, guys, or audience? Other WaterSoftHack flows? Okay, all right. Okay, thank you guys. Great job. Okay, let's move on to the next group. We have remote sensing group. So if you guys ready, you can start at 11:30. You guys check your presentation, so make sure that everything works. Have 2 minutes to make your stuff up. If you're ready, you can share your screen. You have less than a minute.
I just shared the screen. Can you all see?
Yeah,
You guys can see it. Yes, let me check it. My system is a little bit tricky today. Okay. Yes.
Okay, nice. So I'm going to start now.
Yes, give me
Okay, sounds
few
good.
minutes. Few seconds.
Okay, sounds good.
Yes. All right. Okay, again, you guys have 10 minutes time to present your work, and then after that, we have Q&A questions. We try to be 5 minutes, but sometimes it can go a little longer, but it's okay. So you guys can get started. Yes, go.
Good morning, everyone. Imagine trying to manage groundwater resources when the data you rely on is so coarse that it can only tell you the situation for an area the size of the small country. That's the challenge scientists face when using GRACE satellite data, and it's exactly the problem we set out to solve today. So our project, downscaling GRACE data for local groundwater monitoring using random forest and LSTM, was developed by Hussein, Assis, Neda, and by me, with the guidance from Dr. Vidya Samadi. And so this is the extreme precipitation pattern for the global scale, in the arid region. So we found several studies. They have conducted their research in different areas, but there is a lack of studies in Arizona state. So we are trying to do the downscaling of the GRACE data for the Arizona state, one of the arid region. So GRACE data is gravity, recovery, and climate extreme. So it is a very low resolution image with 300 kilometer. So here we are using the high predictors with high resolution. So we can develop the model from that and then use that model for finer scale estimation of the terrestrial water storage. So for this, there are different model availables like the LSTM, random forest, and so on. But in this study, we use the two model, the LSTM long-term short memory and the random forest. So long-term short memory is like used in the hydrological time series and non-linear sequential and used for non-linear sequential pattern, and also used for temporal complexity. And while the random forest is very popular for the spatial downscaling non-linear relationship and for the high dimensional and highly correlated predictors, and has the limited comparison for the random use of random forest for groundwater. So Neda.
Thank you. So we did some literature review on previous studies that have used modeling for downscaling GRACE, and they were trying to predict groundwater storage. They have used different predictors, and the root square of root square values is different between 70% to 80% in these studies. Each study uses different predictors, so we realized that the nature of the predictors is not a great, it does not have a great influence on the research. We have tried to use similar predictors. Also, the geographic area is very important in these studies, as climate characteristics can determine the functionality of the model, and the same model may not apply to in different regions. And now Ashish will explain the study area.
Thank you, Neda. So let's talk about our study area. So our study area is Arizona State, which is characterized basically by an arid to semi-arid climate, receiving less than 12 inches of annual rainfall. This limited precipitation drives heavy reliance on groundwater, especially in major urban centers like Phoenix and Tucson. Geographically, it spans the Basin and Range Province and the Colorado Plateau, offering diverse hydrogeological setting. This makes Arizona an ideal location to test our downscaling method, particularly given the ongoing groundwater depletion in the Colorado River Basin, as highlighted by Abdel Mohsen and his research. Now let's talk about data. So basically, we have the predictor data here, grace data, and the ground truth data. So basically, we used 7 predictor and a subsequent result as well, like accumulation stuff. So we took precipitation, land surface temperature, soil moisture, evapotranspiration, surface runoff, and subsurface runoff, and NDVI from various sources, and their spatial resolution are like very fine with respect to the grace, which is of 3 degree resolution, which equals almost around 300 kilometer. So all the data have been temporarily transferred to a monthly scale. Next. So again, this is the data. This is the snapshot of one of the month of December 2009, where there was heavy precipitation in Arizona. So we plotted this as a map. Next. So let's look into our methodology. So what we have done. So our methodology starts with predictor variables like precipitation, land surface temperature, and others. So altogether, we use 7 predictors along with grace TWSA as the input. So TWSA basically means terrestrial water storage anomaly. First, all the data are resampled to 3 by 3 degree grid and normalized. We split the dataset into training. So basically, from 2002 to 2016. So for the period of the past GRACE mission, we use those data as the training data, and for the later data from 2019 to 2023, for the GRACE follow-on mission, we basically used them as a testing data. Basically using 2 model here, random forest and long short-term memory LSTM model, to learn the relationship between predictor and grace. Once trained, the model generates downscaled grace data, which is combined again with the predictor variable and resampled to finer resolution of 0.1 degree in our case. Although we could have like extended to more finer, even to 0.05. But for this research, we just resample to 0.1, and this allows for the high resolution of grace TWSA prediction, which are then validated against groundwater level measurement, which we collected from the Arizona Water Department. So basically, in summary, the framework leverages machine learning to bridge coarse grace data and the finer groundwater insight. Now for further talking about result, I'd like to call on Hassan. Thank you.
Okay, so we started with EDA trying to understand the relationship between the predictors. So first the variance inflation test to see if there is multicollinearity in the predictors, and then we can take some of the predictors out, because initially we had the predictors and we also estimated the cumulative changes in the predictors, for example, in evapotranspiration and the precipitation and so on. And we wanted to keep them below 10, which is kind of the threshold for when you have like high multicollinearity. We also looked at the correlation to see which, can you go back? Sorry. Okay, the correlation to see which predictors might contribute the most. For example, here, especially for the random forest, the accumulated evapotranspiration, because it have the trend, might be contributing the most. Also here, the soil moisture anomaly and the evapotranspiration. Next. So first, this is a result from the random forest model. So the observed here versus the predicted, the correlation is 0.7. It's not very good, but it's not too bad also. The model showed some overfitting. So when we compare the training and the testing performance, there's a difference, and we think this could be due to the few points, especially that the data is monthly. So this might be a reason. Next. However, we continued with the downscaling. So here in the right, you have this is the GRACE GPL on the coarse resolution, and on the left, this is the final resolution from 3 degrees to 0.1 degree. So this is 30 times better resolution, and this is a trend, comparing the trend in both. And this is what we mean by trying to predict or downscale to see the changes in the local scale. So for example, in the southwestern of Arizona, this is close, I think, to LA, there is high depletion in groundwater there. Next. This is also, so after after downscaling, we upscaled the final resolution changes in terrestrial water storage all the time series to their coarse resolution, and we compared the correlation, especially between the observed and the predicted in the coarse resolution, to see if the downscaling has changed, for example, the pattern or the trend of the data. But to some extent, there is high correlation between them, so the downscaling didn't change the nature of the data. Next. Then we tried the LSTM model, and we know probably this is not the best LSTM result that you would like to see, but we applied a model for each pixel. So these are 9 pixels that are covering the area. We found that, for example, in the first 6 pixels, the performance is really bad, but it started to improve in the last 3 pixels. And we have some ideas on why this is happening. So the model is struggling to learn. This is probably because of change or the distribution of the data in the training period is different from the testing period, especially that Arizona is an arid region and it relies on extreme precipitation events that change the terrestrial water storage. But here, where we have in the last 3 pixels, where we have clear seasonality, especially in the last one, this is where we have the highest NSE. And the one also before, so 0.6 and 0. Also close to 0.6. This is probably because of the seasonality is defined better, and the model was a little bit able to capture the changes here. Next. This is also the relationship. It's bad, but we want to see the scatter plot of the data. This is where we have the bad predictions. So it's not very good, but I think it can be improved later. We can change the structure of the model. We can also check for the data distribution to know why this is happening, especially for the LSTM model. Next.
So we have some future directions and planned improvements for random forests. We can apply residual correction to the GRACE data. For LSTM, we can apply adaptive feature selection for each model. We can also change the lagging from 0 to 3. And also we can use finer resolution predictors. We can also drive groundwater storage to validate using real data. And our key findings is that GRACE data could help in capturing groundwater storage data in regional or local scale. LSTM is promising for capturing temporal variability in areas that are that don't have enough data, and in arid areas, both RF and LSTM are data-driven models that can be used in plus to the in situ measurements for groundwater storage monitoring. Thank you. And we want to thank the WaterSoftHack team and Dr. Samadi for their help and training, and we'll take any questions.
Okay, great. Any questions for the team? Can you guys hear me?
I have a question.
Yes.
I hope this doesn't come back to bite me, but if you had more time, how would you have like attempted to address the scatter of your data? Or do you think it's like that's the best the model can do?
No, not really. So there are a few things that we wanted to do, but we didn't have time. Like we struggling at the last few hours trying to change it, but it didn't. So first we used the same predictor, especially for the LSTM model for all the pixels. So it's the same predictors for all pixels, which is everyone is a different model. So what we wanted to do is to make the model more flexible, so that it chooses the predictors that are best for each pixel, and then the prediction probably is going to be better. At the same time, there is lag time between, for example, precipitation and the response of GRACE because of the nature of GRACE and its monthly data, and they take the mean from a few measurements over a month. So when if we could do this, and this is we think with the lag time, this would improve also the model. So we have the lag time, we have also choosing the predictors. This could improve the model a lot.
Great, thank you.
Okay, any other question?
Yeah, I have a question.
Yes.
Can you go back to the evaluation that you did by comparing correlation between the original and the reconstructed data?
Yes.
Yeah, here. So, it seems like, there are some reasons that are well correlated and the others that are not. Like, did you try to understand what was leading to that discrepancy?
You mean here, for example, the northeastern one here?
Yeah, sure.
Yeah. No, we didn't. We didn't do this.
Okay.
I think, yeah, there are a few things that should have been done to, to understand why this variance, but we didn't have time within this.
Sounds good.
I think the problem with us was we try to hyperparameter. We try to change the parameter time and again. So our time most of the time was changing the hyperparameter. That was the problem for us.
Sounds good.
Any other question?
I have a question.
Yes.
Have you included the soil moisture remote sensing data, like the SMAP?
No, what we included, the soil moisture, was from the FLDAS. It's part of the FLDAS model, GLDAS model. So it's land surface model data, not satellite data, and it considers the first 2 meters of the soil moisture.
Okay. Because as I'm on knowledge, the soil moisture data have a great influence in predicting the groundwater.
Yeah.
Maybe if you include more precise data, that will improve your modeling performance.
Yes. So if we had also more time, so the data that we use, for example, from the land surface model, FLDAS here, there's other land surface models that has different data, for example, groundwater component that we could have used. But we were trying to, because, we will have to download a lot of data, so we kept what we have for now. But yes, usually we should try different land surface model data and see which would be represented better in this area, because the land surface models are different from one area to the other. So we should compare different models and see which is better. Yes.
Great.
Thank you.
Any other question you guys may have from the group? You can also enter your question in the chat. Okay, great job. I have a quick questions. So, any of you can answer my question. So the first question is about the resolution that you had, your data with different kind of resolution. Some of them were fine resolution, some of them coarse resolution. So how you guys justify this when you incorporate into the neural network model?
So first, before doing anything, we upscale the data to the coarse resolution in the training. So first we upscale all the data to the 3 by 3 degrees, and then it's the same. So each pixel has a time series for each predictor and the target, which is grace. And then in the prediction, we also have the structure of the data. So when we obtain, when we train the model, we put the predictors, the same predictors, but all on the 0.1 degree, because we have most of them around this resolution. So it worked this way. So with the same statistical relationship that was found on the coarse resolution, we use this same statistical relationship or same model on the final resolution predictors. So we obtain grace on the final resolution.
Great. Okay. So you use two algorithms, random forest and LSTM.
Yes.
So my next question would be how you guys came up with this selection. If any other members can answer it, that would be great. So what was the kind of logic behind using LSTM versus random forest?
So basically, what we were doing was we took almost 2 days to do the literature review, and most of the research was doing this random forest, using the random forest, and LSTM was like limitedly used. Although convolution LSTM, combining the LSTM was used in some of the research. Most of the research used basically the random forest. So we try to like compare the LSTM what we learned in this workshop with the the random forest, which was like used by many researchers.
Great. Okay. So how you've set up your LSTM model? How many layer you had?
Okay.
You don't know the
So
hyperparameter.
yeah, so in the hyperparameter, in the optimization, for example, the number of layers, we tried 1 and 2 layers. Also, we tried the ranges, for example, the dropout between 0.2 and 0.6. We tried also the hidden size as categories. So we tried 3 numbers. We tried to make the model less complex and then increase the complexity. So also the batch size for 16, 32. So we tried different things in the hyperparameter optimization.
And
So it's
also
all
we like use the EPOs of around 200 up to 300 for some time, but it didn't produce like very good result.
Okay, great. So Sanjeev, can you let me know how you have with the LSTM setup if you done, and then with the parameter optimization of the LSTM, how many parameters you had, and how you guys optimize the parameters during your run?
For the parameter optimization?
Yes, for LSTM.
LSTM, right? Yes, like we use like different the approach and the different like the batch size and the sequence length. We parameter like we did like different tuning of the sequence length for the LSTM, and then we also like did like different like approach for them, and then we parameterize.
Okay.
Yes.
Okay. Thank you.
No.
So, and then I asked the same question to your group. What was the, some of the challenge you guys faced during, executing this project? Could you
The main
elaborate?
the main challenge is the time.
Mhm.
Yes, time is the one of the main challenge, because when we run, sometimes it took like 1 hour, 2 hour for we want to divide the study like the pixel, divide the model for each pixel, and it was like completely impossible. It was showing around like 3 hours, 4 hours, and then the time is increasing. That's the major challenge. Like yeah, also tried to run in the Palmetto, the Clemson computer, and it's also like not working on the Palmetto also. So yes, that's the major challenge.
Okay. So
I
have
think-
you
Sorry.
tried to use NAIR resources?
No, I just use the Palmetto. No, not the Near. I think the Hassin, did you use Near?
no, I didn't. No.
Okay.
So another problem was the data. So we had huge amount of data, like almost 50 to 60 GB of data. So because it was like 7 predators, 1 grace data from 2002 to 2023. So so what we did is we ran the model in 2 computers, in one Hassan and in mine. So we basically used the HPC that was available in our university. So that was the main thing. So the data was like quite a lot.
Yeah.
Okay. What else?
Yeah, I think one other thing that I'm just gonna say this because it could be like applied for the next year. Like if we were able to meet in person and work together, that would be better. If it's remote is like we would be miss some sort of connection, you know. And exactly what Ashish said, like we had a lot of data, like 60 gigabytes, and that was like a time consuming for each of us to like try to run the model. Like I think I also tried, but like we each faced issues that I think it could be communicated better and worked better if we were, you know, working in person.
Okay, great.
Also, one challenge we had, it was mostly that we invested all our time in on the model, especially on the optimization, when the result wasn't very good. So most of the time was invested on this, so we didn't have much time to like evaluate our results. So this wasn't from our side, but yeah, we tried our best.
Great. Okay, any other comment from audience? Any question, feedback?
I think one of the like important thing, if we could have like given 1 day for like image analysis or something, because we only did for like the time series data, point data, you know. So if we have done like the analysis for image data, so I think it would have like made more easy, you know, for us.
Yes.
That is
Okay.
it.
I actually have one question. I had
Yes,
this problem with running GPU on Google Colab, and their access really helped. So thank you for that one. And I have a connected question. Let's say we want to work on this project later on. Will we still have this access to Nair?
That's a great question. So I have access, you know, my proposal is not proposed, scope of work was approved for a year to use
Mhm.
resources. So we got approved in early January. So it finished, I guess, end of December, early
Okay.
January again. So you guys would be able to use it to the end of December.
Mhm.
And then since we are going to conduct this kind of WaterSoftHack training again next year, I'm going to reapply
Mhm.
for the NAIR resources and then see how I am going to see how much credit they give us. But yeah, for sure, till the end of December, you can, if you want to use it for your teaching, we would be happy to help you to adopt WaterSoftHack package in your teaching. If you want to teach any of those algorithms in your courses or in your research, we'd be happy to help you, but you guys can still use it up to end of December. I hope that the credit is enough for you to run the models. But after that, I have to reapply it and hopefully we get approved. But yeah, that's, you know, every year we have to reapply it and then apply for credit every year. Yeah, so
I see. Well, still great. Thank you.
yeah, you're welcome. Any other question you guys may have? Okay, let's see.
I think Sanjeev can stop share the screen.
Okay. Alrighty. Okay, hydroback team is the next group. You guys start at 12 o'clock sharp. You guys you are here, you ready?
Do you want us to wait 2 minutes? Do people need a bathroom break or something?
Yeah, if you can, you want to use, you know, have a bio break for 2 minutes.
Yeah.
Then you start at 12, then that would be great. Okay, you guys have a few seconds to get started. So let's see, all of you are here, right?
Yeah.
Okay. Okay, you guys can get started.
Of course. Okay. Thank you for joining us today for the WaterSoftHack capstone. Our team, Hydroback, is a group of four, Adi, Claudia, Maral, and myself, Mohammed. So in this project, we performed an experiment to infer catchment average precipitation by doing hydrology backward, and that's by leveraging deep learning for minute scale QP or quantitative precipitation estimates. So the main problem that we are addressing is a common issue in operational hydrology, where we still fail in estimating or predicting floods and high water levels, and we all witnessed what happened in Texas on the 4th of July. So basically, the problem that we are addressing is stemmed from a limitation when it comes to the calibration and of data-driven methods, or while doing hydrology in the old-fashioned where we train or we calibrate physics-based hydrological models. And this limitation is simply we don't have data sets that they have enough temporal resolution to capture flood events, that they have a rapid onset similar to flash floods. So we are all familiar with camels, caravans that comes in daily or sub-daily temporal resolution, but we don't have really data sets or benchmarks with minute scale forcing data. So based on very well-known research by Keith Bevan and Stuart Lane, they propose that while developing models, we need to do it for a purpose, and we need to fit those models for that specific purpose. So if we really want to forecast flash floods on the minute scale, we need the forcing data at the minute scale rather than having rainfall, for instance, coming on the hourly scale. So one opportunity that could be leveraged to develop a benchmark that relies on high temporal resolution rainfall dataset is the MRMS dataset. So it comes in 2 minutes temporal resolution. So with this being said, if we have 2 minutes rainfall, probably we can perform streamflow nowcasting. Probably you are familiar with rainfall nowcasting, but also it could be valid for streamflow, and that's one way to improve the estimation of streamflow on a minute scale. But the limitation here that we don't have radars everywhere. So the white spots that you are seeing here, those are areas in the United States, basically in the CONUS side, where we don't have radar coverage or we have poor radar coverage. So this is a limitation to apply those type of research or operations in hydrology. So the main question that it's driving our research here, can we leverage data-driven methods to help us estimate QPE by doing hydrology backward? And this is a well-established concept in modern hydrology, where we go from streamflow or water balance to ET or to rainfall as an input for hydrological models. So our main goal is to demonstrate the feasibility of data-driven methods for estimating radar-based QP in under-observed basins. But before we get to that point, we broke down those goals to two objectives. And the first one is to investigate the usefulness of machine learning-based approaches to estimate catchment-based average precipitation while using the streamflow as a main predictor. And our second objective is to understand the model performance across temporal and spatial scales, considering that we have diverse hydroclimatological conditions across the nation.
So to do this, we've taken the MRMS layer, which is our target, and we have tried to determine a study period using the availability of that data, as well as freeze thaw and soil moisture data, ET, and leaf area index. And there's the soil moisture and the ET and the leaf area index are all satellite data. So we have a mix of satellite and radar data. And from this, we've determined 9 water years that are in our study. And so we've also looked into the Gauges 2 data set, and we started with over 9,000 gauges and then narrowed that down based on whether they're considered reference watersheds and if they have a period of record over 20 years. And then, so that brought us down to about 1,500. And then we looked at all of them that have 100% radar coverage to use for training our model. And that's over 600, but for the purposes of time and considering how big the radar data is and how long it takes to download, we chose 4 watersheds that you can see there. And so they all have different attributes and are different sizes. We have a headwaters in Maine, a montane watershed in Georgia, and a lowland watershed in Vermont that goes out into Lake Champlain, as well as a pretty dense and large watershed in Oklahoma. So those are our study areas. And then, so we created this framework to show you how we designed and prepared the model. We had to do a lot of cleaning of data and scaling of it just to get it ready to go into our 2 different models, the LSTM and Transformer, to be able to run and evaluate it to make sure that we were getting the results, the best results we could before explaining and using the model.
Cool. So as we've all learned over the last 2 weeks, there are many options to choose from when developing an LSTM model, one of our choices. Here we show a conceptual diagram of an LSTM cell showing the input, output, and forget gates, which makes working with sequential data such as time series ideal. So for the LSTM's model head and model class, we use the min-max scaler, which is a common choice for scaling as it normalizes data to a specific range, typically 0 to 1. Next slide. Additional model specs are seen here, but the key point is that we chose RMSE at the very bottom as the loss function because it is ideal for capturing peak rainfall, given that it quantifies the average absolute error of predictions, making it sensitive to both large and small errors, which we want to identify. Next.
As for the transformer model, we use 7 dynamic and 7 static features. All features were normalized with a min-max scalar, except for precipitation, which were smooth using the 7 interval moving average. On to time constraints, we use a subset of data for higher parameter optimization using Optino, 23 parameters, learning rate, dropout rate, and rate decay. To better understand the model's performance, the selection of the evaluation matrix is based on a purpose. And our objective is targeting the correct time and magnitude of the peak rainfall. So RMSE and NSE were selected. Okay. After model training, we investigated the performance of the training period. This figure shows the temporal variability of observed and simulated rainfall time series at the main site. Overall, the model underestimated low precipitation values while capturing high-intensity rainfall events more accurately. Next, please. This figure shows monthly RMSE of all sites using LSTM model. The highest RMSE was observed in October, which is a seasonal transition month across all sites. This may be due to the fact that extreme regimes respond to seasonal rainfall changing with lag, and the model could not capture these transient dynamics well, leading to larger prediction error. Here is the transformer model performance. The transformer model showed better estimation of overflow rainfall volume, but it did not adequately capture peak values, which is an important limitation when modeling flood extremes. As of today, here are all results of we have in hand. So, as I mentioned, transformer outperformed LSTM model in a predictive accuracy, which aligns with other studies. However, both models achieve NSE scores below the generally accepted 0.7 threshold, indicating room for model improvement. Overall, the results showed the promise of deep learning models for predicting catchment average precipitation. Next.
All right, so to wrap this up, we learned this week that having the code for an LSTM model is not enough. Even though the LSTM model is a very strong model to use, we definitely need more information, such as what model, what parameters to input, and how to address issues or unexpected challenges. Here's our Gantt chart showing how we tried to address this, but obviously we came up with some issues and challenges. So as we all know, large data sets require a lot more time to manage, while on the other hand, being data restricted means expanding the search for data, which may then require more pre-processing. So finally, also user awareness of LSTM architecture and computational cost makes a big impact on successful model execution. Next slide. So we want to end with next steps, which we can now pursue with more time next week after we all get some sleep. Next steps include reflecting on our modeling approach to see if LSTM or transformer models can be improved or if other models might work better. We also recognize that all models have limitations. On the data side, we're looking into better selection of data, more sources like NextRad, longer time series, and maybe experimenting with model input size. Another consideration is to choose a different model or run sensitivity analysis with comparisons, including physics-informed or transfer learning approaches. Finally, we're leaning on support, so using online resources, publications, and collaborating with WaterSoftHack team to help us in this next period. Good. Sector references, and then just want to say thank you all for your time in listening.
Great. Okay, great job, guys. Any question from the team? Any question?
I have a question.
Yes.
Did you guys, try to, I know, you didn't have a lot of time, but did you try to think about, why the models were specifically missing the low precipitation values while being decent enough in capturing the high intensity?
Which model, the LSTM or the transformer, or both?
I think that it was
Only
LSTM.
LSTM, only.
Can you go back to that slide, Mohammed?
Oh, and was the trend different for uh, transformer? I didn't see a similar plot for transformer. Okay, yeah, you can
No,
see it. It's the blue
yeah,
line.
the problem is mainly for the LSTM. While I don't consider it as a problem because our purpose is to capture peaks, so that's our target. I mean, we wanted to do this kind of non-guided training, so to see what the model, how it will perform. This being said, the small values that could be underestimated, our guess would say that when we have large changes in the stream flow, and that's our main predictor, the model is able to capture those changes in the rainfall. But if we get to small changes in the stream flow, even if you have small rainfall, you may not see any changes in the stream flow, and that could explain that. In order to elaborate more, and that was, I mean, a very obvious observation that we saw when we got those results. So directly we computed the errors over the monthly, over months of the testing periods that we get, and we saw that the errors that are always, I mean, small, between, I would say, between 0 to 6 millimeters per hour. This is an aggregation version of the hourly 15 minutes rainfall that we have. So this being said, small errors are dominant, and the reason because the model cannot capture those small deviation in rainfall where we don't see major changes in stream flow, and that's basically our target. If we could reproduce the peak rainfall, that really could have a pathway to create a benchmark for training models designed for flood prediction.
So, did you like see a similar pattern in the transformer? Like,
in the transformers, we did not see similar patterns. This being said, the way that the transformers and the LSTM were designed, it's a little bit different. I mean, it's and the results they look at, they are the opposite, totally comparing to LSTM. And probably here we can say that there is a synergic use between the LSTM and the transformers. I mean, you can compensate for the errors that are generated by LSTM using the transformers. So even the training methods and the way that the pre-processing was addressed for the transformers, and Maral could elaborate more on this. It's different than the LSTM. And the rationale is simple. We tried one approach for the LSTM, another one, I would say, bit random for both. And we just wanted to see how the models they would perform.
okay. Thank you.
Thank you.
Great. Any other question?
I have a question.
Yes, Neil.
My question is about the rationale of your work. Since we are mostly trying to predict the stream flow, which is the model response variable, and I'm wondering that if you have the stream flow data, then the rainfall event must have already occurred and measured by the sensor.
Sorry,
And
Nima,
this
can I stop you? So you just said that we're trying to predict stream flow. Do you mean predict precipitation?
No,
Can
I
you
mean that
restate what you're trying to say?
because there is a delay between the occurrence between the rainfall. The rainfall goes and the response of model is going to be the stream flow. I just want to know the rationale of your work, because you
Thank
have
you.
already the stream flow, and then
Yes.
when you have the stream flow, then the rainfall occur, the sensors are exist and measure the rainfall. Yeah, I just want to get to know the rationale behind your
Yeah, I
your
definitely
work.
recommend that you read a couple of the papers that Mohammed cites. I'd say hydrology backwards can be kind of abstract unless you think about it. I think we take
I know
predictions for
I know
granted. So
that
I'm gonna let Mohammed talk a little bit more about this.
okay. Yeah, I know that even the WR paper that you shared by Krishna, he's a great hydrologist. I read that work as well, but about that that hydrological modeling, because your approach is different. About that hydrological modeling that he used, I think that makes sense. But about this ML approach that you use, it's completely different.
It's
I
different.
just want to, you can talk about
Thank
it and we can discuss more together.
Thank you, Nima. Now we can take our time. So let me start with asking you. So when you train your models, what do you use? Usually, which data set do you use? Camels, maybe?
Go ahead with your explaining. Okay,
I mean,
I will
yeah.
answer
So
you back at the end.
let's say that when you train your model, use the camels, caravan. There are a couple of other data sets out there, but they come with hourly or daily time step. So for instance, camels, let's focus on the camels, which is one of the most used data sets in the US. Before that, there was another one developed by NOAA. So in brief, all of those data sets, they come in daily or hourly time step. So when you train your LSTM model, or even if you want to calibrate your hydrological model, you are targeting events that they are on the daily or hourly scale. Okay. So our purpose here is to create something similar to camels. So camels, when they created this data set, they went to NLDAS and they put NLDAS as the rainfall. So what we want to do is to have stream flow, and for people to start creating models that are able to predict stream flow, they need rainfall on the sub-hourly time scale. So that's what we are trying to do. Now, the problem is that we don't have high quality rainfall everywhere. So our target is simple. We say at those locations where there is very good radar coverage, we'll take that rainfall from the radar. We trust that's our high fidelity data set. And we take the stream flow at those gauges and we try to do things backward. And the intention is, if we are able to calibrate such models, then we go to those white spots if you can see them, where there is very poor radar coverage or there is no radar coverage at all. And we use that same LSTM model, which should be trained on different hydroclimatological conditions and estimate rainfall there. When this is done, hopefully, we can come up with a data set similar to camels, and we say the time is 15 minutes for stream flow and for rainfall.
Okay, you are talking about the camel data. You know, I'm not talking about the data set. I'm talking about the decision maker. You know, the decision maker. When you are looking at a decision making, you need the real time. You know, data. You know, the camel data is already done. I'm not talking about the data sets. I'm talking about the approach of, you know,
Yes.
just
So the
going
decision
on.
making, let's put it in simpler words. The decision making, let's say it's NOAA. So NOAA, for instance, when they developed the national water model, now they are developing next gen or whatever models they developed during their RFCs during the years, they're using benchmark data sets to calibrate and validate their models. So those benchmark data sets, camels X, Y, Z, they come with daily or hourly temporal resolution. So my goal is not to forecast. My goal is to provide a data set that those decision makers or operational agencies can use to create models that they could serve for operational hydrology.
Okay, because it's going to be a long discussing, but I will stop here.
Well, I don't see
If
what the
you
discussion
yeah.
is. I think there's a
Yeah.
misunderstanding where you're questioning our
No,
rationale, but
no,
we
it's
clearly
not
have.
misunderstand.
You just said that you're questioning our rationale. So I think maybe that sounds like you need to do a bit of a literature review in terms of backwards hydrology before you you know, decide to question our methods.
Yes. Okay.
I just yeah, that's
Okay.
all. Yeah.
Okay, Nemo, great question, great discussion. That's what we want to see. So you guys can have offline discussion, use private chat, or email. So any other question you guys may have from Hydroback group?
I have one. Since
Yes,
we are working on
Corinne.
the similar models, how did you approach setting up the sequence length then? Because that was one of the main challenges for our data, like which sequence lengths to choose. And so what did you do? Like, I think you had like 24 as a sequence length for one of the models, if I'm not mistaken.
Yes, you are right. So we listed those, and basically we tried to mimic some of the physical processes and the temporal variability that would be captured in a watershed. So the length was 365 days, that's a year. And the patient length, that was 30 days. There is another thing that we want to mention here that was, I think, a little bit relevant to us. I mean, there was the warm-up period also, I think. This was removed, but the warm-up period also was 30 days, 1 month.
Okay, thank you.
And it was kind of a blank slate at the beginning. You know, we only show what we ended up using, but we did consider other epochs. We considered other types of warm-up periods. But as you know, because of time and just trying to get them running, we kind of end up with one. But a sensitivity analysis in the future would be helpful in addressing if that is indeed the best or if there are better options out there.
Okay, thank you.
Great question. Any other question you guys may have from the team? Okay, so let me ask you guys maybe 2 quick questions if you have time. So how your prediction went from you know, headwater stream going to middle size to larger scale, you know, the performance, how the difference, you know, went from, you know, small scale going to larger scale, and how the parameter kind of optimizations gone in this process as well. So could you elaborate a bit about those things in your modeling setup and performance assessment?
Let's see, we have it in the paper. There's a
Yeah,
table.
it's
As you
the
know, Vidya,
table.
we showed you a table of a paper that shows the length or the area of all the sites. So you pointed out that they're all different, and that could actually introduce some kind of complexity that the model can learn from, which is great. I think we definitely could have done like a feature importance analysis to see if there were some features that were more important than others for these 4 basins. But we definitely didn't, apart from having them and their data, we didn't really look at how having each watershed like affected our performance metrics. And I think that obviously if we were like to submit this in a paper, we would have to get into that a bit more to increase the quality of our work.
Yeah.
May
and
I add something? May I add something?
Yeah, absolutely.
Yep. I added a table in the chat, the image in the chat. If you could, I don't know if you could see in a
nice.
Yeah,
Yeah,
I was
the
just
thing is that
thinking.
when I'm looking the amount of rainfall and the NSE, the higher the amount of the rainfall, the higher the amount of NSE. So it was in the papers also using this idea of hydroback because when the system changes, soil moisture decreases, the hydroback had some problems, and the new versions added some new parameters for accounting for soil moisture. We are putting the soil moisture data, but our data set may lose some data. So the higher the precipitation, the better results we got. I don't know if you could see but it's also in your email.
Yeah, so you see a like direct correlation between like higher kind of precipitations and better performance. Okay.
Kind of, we did not get to final conclusions based on 4 basins. We tried to, while designing the model, we tried to have, I would say, a foundation to have those analyses later on, and that's by considering static parameters. So the LSTM was fed with the dynamic parameters and also static parameters, which are the basins attributes and some hints about the hydroclimatological conditions of the basin location. This being said, when we got those 4 basins, I mean, we tried to have this diverse setup of the basins, but it's a little bit difficult to have final conclusion that for bigger basins we have less performance or based on the rainfall. Those are observations. I fully agree with the team. But once we get to more data sets and more testing, I think we can get a better idea about how the response of the model to those changes in hydroclimatological conditions.
Okay, so again, I have the same question, but maybe in different format. I ask. So if they give you another chance to do this research again, what approaches would you do differently and why?
Well, I think we well at this point, since we did it already, we would kind of jump off from here, and that goes to my last slide about the next steps, and it's also in the future directions section of the paper. So we noticed in a literature review that other studies actually couple machine learning technologies. So they'll do hybridizations where maybe they consider wavelet transform, which is a big option, or like a strong option for applying to series decomposition and extract temporal features for streamflow and rainfall prediction and forecasting. We also noticed that other LSTMs actually combine themselves with like ARMA, which is something that we learned in the first week, but didn't have the chance to apply. So that's something else that we would love to consider. So the fact that LSTM is like so flexible and like kind of able to work with most other models means that we can actually, instead of starting from scratch, build off of it and see how it can improve but not first the performance metrics, but also trying to eventually identify the physical understanding gaps that we have and then addressing them.
May I add something?
Sure, go for it,
Very
Mara.
quick.
I would like to add some sort of lag time based on the time of concentration of different watersheds. And also, I don't know if we should add static characteristics like this. And it's a discussion that I'm going to have with you later.
Yeah, we've had that. Yeah, we'll talk about
Yeah. Yeah, typically a static variable doesn't make much differences in the performance compared to dynamic variables when you add
Mhm.
as a feature. But yeah, you could try it and see. So if you guys encounter any difficulty using WaterSoft package, could you please put it in the chat so we don't have time. We've got to move on to the next presentation. Okay, next presentations, drought and risk. You guys are ready? Could you quickly share your screen? Meg and team.
Okay. Just doing a quick mic check. Can everyone hear me?
Yes. Okay.
And is the rest of my team good to
Yes.
go?
Yes. You guys good to go.
Good to go.
Yes. Go.
Awesome. So, hi everyone. My name is Sophia, and I worked with Ethiopia, Meghana, and Damien on our project this week titled Simulating Streamflow Drought with LSTM and Transformers for Risk-Informed Reservoir Operations. And during our presentation today, we'll provide you with some background and motivation for this project, talk a little bit about our selected study area, go over the data and methods that we used, highlight some of the results we found, and then discuss our conclusions and acknowledgements to the program. So drought is one of the major hydrological extremes which occurs globally, and these events occur as a result of decreased precipitation, increased temperature, and increased evapotranspiration. Drought events impact various aspects of the water cycle and can be divided into 4 different subtypes, including hydrologic drought, agricultural drought, ecological drought, and socioeconomic drought. And these drought types are designated based on the impacts of a particular event. In this study, we are focusing on hydrological drought, which affects the water that's available for stream flow, water quality, and also causes reservoir levels to decrease. One of the reasons we focused on this type of drought is because the impacts directly affect the water that's available to support human demands as well as environmental demands. Droughts directly impact reservoir operations because when there's less water available, then reservoir managers need to respond. Decision making for reservoir operations is also driven by water supply, flood control, different water use applications, navigability requirements, and environmental flow requirements. Here I'm showing an example of a drought of a reservoir that has experienced stress due to drought conditions. This is Lake Powell in Colorado, and you can see that beginning in the late 1990s, there was a drought that started, and it's caused shrinking of this reservoir over the last 2 decades. And so the problem statement that motivates our project is really that the complexity of the anthropogenic factors that drive decision-making for reservoirs, combined with a lack of early warning systems for hydrologic extremes like drought, leads to poor management of these reservoirs. And so I'd like to highlight one of the reservoirs in our study area and kind of show an example of what we're trying to inform in this project. And so the red shows streamflow drought index values, and then in green we have reservoir storage, and in orange we have reservoir release. And so what we're really focused on is seeing if we can use a combination of baseline reservoir operations and predicted drought index values to improve reservoir release timing and thereby improve resilience of reservoirs to drought. And so we focus on 3 primary questions in this project, which are what are the baseline for reservoir operations? Can we leverage different deep learning approaches to predict streamflow drought? And then how can we use those predictions to inform improved reservoir operations? The selected study area for this project is the Upper Colorado River Basin. This river basin supports more than 40 million people. And it's also quite interesting because it has a diverse climate. The northern part of the basin has pretty high elevation, and the streamflow is mostly driven by snowmelt. And then the lower part of the basin is arid and canyon regions. So we got all of our data from camels and the corresponding streamflow gauges. There are only 24 gauges within the Upper Colorado Basin. If we were to do this again, we would probably revisit our study area, but the main reason we focused on this is because of the amount of reservoir data in this basin and the effects of management in this basin. So we really wanted to focus on like an area that had a lot of reservoirs, had a lot of reservoir data, that we could really explore. And so the results that we highlight in our presentation are for the Taylor Park Reservoir, which is shown here in black, and it's just directly downstream from a camel's catchment, which is one of the reasons we selected it. And then the main water uses for this reservoir are irrigation and recreation.
This is the overview of our methodology. So the first step is the data collection. So we have been using CAMELS data, USGS stream flow, daily meteorological weather, and rice reservoir data. So then we do the data processing. We extract the data for 24 catchments. We did the quality control, and then we prepared the data for training, validation, and test split. So the training is done for 1980 to 2010, validation from 2011 to 2019, and the testing from 2020 to 2023. So we trained the model. We have considered two models in this study. That is the entity-aware LSTM model and the transformers. So then we do the model evaluation and selection based on some of the metrics like NSC, KGE, correlation, and MSE. Then we calculate the SSI from the predicted stream flow. Then we do the adaptive reservoir management development. Sophia, can you zoom out? Yeah, thank you. The next slide, please. So this is our model configuration. So as I said, we have been using entity-aware LSTM model. So this is a variant of standard LSTM model from Google's neural hydrology package. The question is, why are we using this model? So since we were only focused on Taylor Park, why are we considering all the 24 catchments? To answer that, so never train a LSTM model using a single basin. That's why we thought we'll train it on 24 basins and see how it performs. So coming to this, it is a LSTM variant where the input gate is controlled only by static attributes while dynamic inputs are derived by other gates. So the purpose is to encode the basin attributes into the memory update so the network adapts dynamics by the catchment. So and also we consider the transformer. So in the transformer, it is an encoder-only architecture. Unlike LSTM, which processes step by step, it uses a self-attention mechanism and it looks at the entire sequence at once. So even the transformer model, it considers both the static and dynamic attributes. Next slide, please. So this is the model configuration. So we considered, we wanted to define the hyperparameter space. So we considered the learning rate and output dropout and hidden size and the batch size. We did a certain trial and errors, and these are the hyperparameters we chose for the LSTM and transformers. Next slide, please. So these are the performance metrics for the regional LSTM model across the 24 catchments. As you can see here, when it comes to the overall skill, the correlation is about 0.85 for most of the basins, and NSE is about 0.6 for majority, and KG is 0.7 in there are top performing basins. There are also few underperforming basins. So we try to see why it is performing well in few basins and it is not performing well in some of the basins. So what we observed was it is the shared trials, the catchments where it was performing low. It has small drainage areas. It was mainly forest or shrub-dominated land cover. So this caused higher infiltration and delayed runoff. And also we saw that there were metric sensitivity issues like NSE and KGE that penalize small errors heavily during low flows. For example, in basin 9306242, there is very low MSE but negative NSE and KGE. So the main catchment we are interested is in the Taylor Park Basin. So what the similar results were observed for the transformer as well. We'll see the comparison. Next slide, please. So this is the time series comparison for the simulated and observed flows at the Taylor Park. So we have both LSTM and transformer. As you can see, the correlation was 85% for LSTM and for transformer 81. So we are interested in a NSE and KG, which was 0.64 for LSTM and 0.50 for the transformer. So what we saw was among all the 24 catchments, the LSTM generally outperforms transformer across all metrics. And also both the models, they showed poor performance in basins with low flows. Next slide, please.
So using the outputs generated from the LSTM streamflow data, we calculated standardized streamflow index. So like Meg said, we selected Taylor Park River because it's one of the main tributaries flowing into Taylor Park Reservoir and has serious implications in terms of affecting reservoir level during drought conditions. So we estimated a non-parametric SSI by combining historical periods with the predicted streamflow from the LSTM. And we calculated SSI, which is shown as a time series here. We found that on average, there are about 2.7 months duration for drought, and the longest duration spanned about 13 months during the 2012 and 2013 period. After this, we saw that the test period between 2020 and 2023 showed drier than normal conditions, where the SSI values were typically below zero, which was a good use case in order to demonstrate how reservoir managers could actually implement this using test data. Next slide, please. So next, I'm going to talk about the adaptive reservoir management system that we're going to draw from the LSTM predicted SSI. So we wanted to show how a reservoir manager would actually use this system in practice. So first, we have the current conditions. So at this point, the manager assesses what the current condition is. For example, a reservoir could have 70% capacity, which puts them in zone 3. Zone 3 might mean that their standard operating rule calls for 103 cubic feet per second release, but by using our LSTM predicted streamflow SSI, they would also be able to see that the drought index shows an SSI of minus 1.2, which indicates moderate drought. So next, we have a historical lookup. So instead of guessing how to respond or just doing a baseline response, the system looks up historical patterns and sees how operators normally handle moderate droughts in the past and how they would manage their 70% storage. From this, we derive an SSI factor and a storage factor. Finally, our adaptive calculation combines everything systematically. It starts with that baseline release, multiplies uses our drought factor, as well as our storage factor, and then finally has an adaptive response. So instead of just following a standardized baseline rule, the manager now has data-driven justifications in order to release less or release more, depending on what that drought index or predicted LSTM predicted streamflow SSI provides us. Next slide, please. So we applied this in our case study where we saw a differentiated response using the adaptive reservoir release rule. So we found that there was conservation during drought periods. So for instance, during moderately dry and mildly dry conditions, we were able to see about an 8% increase in storage or water saving in our reservoir. And then on the other end, during wet conditions, we saw that there was more water being released. So the plot essentially shows that in drought conditions where the SSI bar plot indicates red, we see that the adaptive reservoir response would be lower than what the baseline condition for that period is suspected to be. Next slide.
To wrap up, the LSTM models demonstrated a strong predictive skill across most of the basins with high correlations over 85 and strong NSE values over 0.6 across the majority of catchments.
The LSTM consistently outperformed the transformer models in most of our evaluation metrics, maintaining a more stable performance across those more diverse hydrological regimes. The demonstration of the LSTM predicted streamflow for that adaptive management conservation conserved about almost 6% of the total capacity over 48 months at the Taylor Park Reservoir. For applications, the methodology is transferable to any CAMELS catchments with reservoir infrastructure, and it provides a drought risk reduction for irrigation and recreation management. And it also demonstrates integration of natural and managed systems in a large sample hydrology space. And for future improvements, for longer evaluation periods and optimized adjustment factors, and then a key component that we discussed was custom loss functions and additional predictors between our static attributes, and then real-time implementation and extension to multiple reservoir systems. And then lastly, for ungauged locations, that can be applied through transfer learning. This work was supported by the WaterSoftHack Fellowship. So thank you to the WaterSoftHack team, especially the PI, Dr. Vidya Samadi, and the rest of the WaterSoftHack team for their guidance, and additional thanks to Quasi for their involvement in the WaterSoft program and the resources that they provide. That concludes our general presentation. Here are our references in a QR code and link format. And if you have any questions, we'd be happy to take those now. Thank you.
16 minutes.
Okay, great. Any question? I think I have again difficulty with my system. You guys can hear me?
Yes.
Okay, good. All right, any question you guys may have from the team?
I have a simple question. Can you help me understand? You mentioned that, in the future work, getting it, deployed in real time would be interesting. I would like to see, have you thought about, how would one go about doing that?
In the future work, we suggested real-time development. A modeler could use data from today and a certain sequential time step to predict future values. And once they get future values, they would be able to update all of that information. And that could be considered sort of an operational kind of management decision. So instead of just having some kind of forecast or long-term prediction, this could be more useful if it was operationalized, where we would add new data, update the model, and then construct our time series accordingly. That would also kind of help us see how the predicted drought values are changing over time, and then adjust our decisions based on those. So for example, we were also discussing in our group, and we said that if the SSI value was declining at a certain rate, then adjust the reservoir decision in this manner. So in an operational kind of or a real-time implementation would allow us to have that functionality, and we could derive more meaningful reservoir operations from it.
So do you imagine doing this at a daily scale? Because, I'm not sure how, impactful it's going to be, because, things probably don't change day to day, right? And the next potential challenge could be if the models are not very interpretable, right? So if the predictions fluctuate by too much, it's very hard to attribute that to anything specific that's going on in the reservoir. So I guess it's very open-ended question, but if you have any thoughts on these kind of things, could you share?
I have
Okay.
one thought, at least for reservoir management. I think a big use case depends on what the water use of that particular reservoir is. So, for example, for a reservoir whose main use is irrigation, maybe reservoir managers are most interested in the pre-crop season or pre-crop planting season. So maybe if we can provide predictions for okay, here's our predicted stream flow for the next 3 months. This is how we anticipate the drought conditions being, they can, make decisions accordingly in line with what their requirements are for agricultural purposes.
Yeah, sounds good. Thank you.
Great. Okay, any other question you guys may have? You can also use chat box to ask your question from the team.
Well, question regarding the application of the method in Camel's dataset. I guess that was one of the Camel's catchments. So with Camel's catchments, they are selected to be natural flow. And is there a value for doing those kind of analysis when you don't have a regulated flow?
Sorry, can you repeat the last part of your question?
So the camels, basically, they are selected to train models because they are natural flow. They are not regulated catchments. So how do you see applying this in catchments without infrastructure? I mean, what's the value that you see to transfer this method to basically to a basin without reservoir?
Well, that's a good question. Yes, that is one of the disadvantages of having CAMELS data because they're naturalized data sets. We considered this to be an addition to those natural data sets where we integrate managed systems. So like we showed in the study area map, just downstream of that specific CAMELS catchment, we have a reservoir, and that reservoir is influenced by those naturalized inflows into that reservoir. So this is sort of an integration of that naturalized CAMELS catchment plus our inclusion of reservoir information and how we could integrate natural and modified flows together. So we considered this also to be an addition to, all managed systems, and they could incorporate reservoir decisions into their naturalized basins. If anybody has anything to add, please.
I would also say that it is an advantage to use naturalized flows for training the model because what we really want the model to do is capture the drought conditions. And if you're using flows that are heavily managed, you're not necessarily going to be capturing the impacts of the drought. You're going to be capturing the management of the drought. So it's actually useful that we have CAMELS catchments for the model training portion of this method.
Yeah, that's a really good question. Because CAMELS, it usually provides us the naturalized stream flow, but it also isolates, how there is effects from dams or diversions in the catchments. So this kind of gives us a, clean hydrological signal of stream flow, which ensures that it reflects hydrological skill rather than, reservoir operating rules. So in the end, what we are doing is the model, it captures the natural behavior, and then we integrate it with the regulated flow data, what we got from the reservoir, and try to make a decision. Yeah.
Totally makes sense. I mean, I appreciate the answers that you provided, and that's totally valid. But just to elaborate, probably because you are in the line of developing things. So, what if the reservoir of the infrastructure is the one causing the drought, especially in the Western U.S.? The target, every reservoir has a target that they need to meet by June 1st, and then they start the releases. But up to June, there is no releases unless there is atmospheric rivers and risk of flooding. This being said, I mean, your approach could be applied to both, but it would be really amazing to see data-driven methods inferring the reservoir rules. So, because those information, we cannot get them. So whatever you are suggesting here could really help in inferring the reservoir rules from the data that you are getting. So, I mean, amazing.
Great.
Thank you.
Okay, any other question you guys may have? One quick question we can have if anyone wants to chime in.
Not a question, but a comment. I'm aware of a US Army Corps program called Forecast Informed Reservoir Operations. And one of my colleagues works there, and I just think like the incorporation of these type of models might, I don't know if they're already using them. I haven't looked into it, but if they aren't, this might be a useful thing for that. So you should look it up, FIRO. Good presentation.
That would be great. Thank you.
There's a bit of literature showing people using LSTMs for reservoir releases out there because drought is a huge issue in the West. So I guess I would like to, all the papers are available to everyone, right, Vidya? I'd love to read how your approach differs from theirs because they use a lot more reservoirs and they obviously consider irrigation factors and climate. So I guess I'm just wondering if a lot of people are doing LSTMs for reservoirs, maybe someone will find a common denominator that helps for everything.
Yeah, great. Yes, all this paper would be available on our website. So I have a quick question I couldn't catch up from your presentation. You guys incorporated the static and dynamic variables, right, into your model. So which one was the most effective or
Yeah,
most effective?
that's a good question. So in fact, due to time constraint, we couldn't do a feature analysis, but I did a quick run using the model with static attributes and without static attributes. And it shows that the static attributes adds to the performance of the model, but when it comes to feature importance, yeah, we can't say like what static attributes are important for what basin. That's one of the limitations, but we would like to work on that.
Okay. So the same with the dynamic features as well, or?
Yes.
Okay.
And also there's another thing with LSTM model. Give it as many data as you want when you have the computational sources. So
yeah.
But we would really like to know the feature importance, but yeah.
Yeah, great. So you said you found that 2.5 months was, if I am correct, was the drought kind of period in your study?
Yes. On average, yes.
On average. So how you came up with that? How did you calculate it?
Yes, we did an average statistics to calculate this. So the most extreme droughts range from about 13 months to about 16 months during different time periods. But if we were to consider the entire time period and then estimate the average length of droughts between 1988 and the end of 2023, it would be about 2.5 months.
Okay, on sequence months.
The drought periods you can see in this plot are just the regions that are shaded in red.
Okay.
So on average, they're about 2 to 3 months long.
2 to 3 months. Okay, great. Okay, could you also share with us kind of maybe Demi your difficulty or challenges that you had in this project or using the WaterSoft package? You use the different kind of neural hydrology package. What type of difficulty you had?
First, I would like to thank the whole WaterSoftHack group and Vidya for the near computational services that made our computation like really easier. So the neural hydrology, it's a good package, but we need to make the modifications. So the difficulties what we faced was like putting the directory part, like defining the parameters, then defining the like hyperparameter space using the optuner. And implementing different models because it comes as a package. The model is already existing. Sometimes you feel like, oh, what is happening inside? So we had to go to the source code and see like how the model architecture is. So that was one of the things.
Great.
To kind of build on that, because of how the neural hydrology package was set up and its internal architecture, between Meg and I transferring files between one another, the file pathing collapsed on itself more than once, especially switching softwares between Google Colab and the Nair server. And that was a lot of our time actually spending rewriting those file paths and getting it in the exact setup that neurohydrology required to run its models. And then outside of the hyperparameters, you don't have much control over the internal architecture. Whereas those PyTorch models that we used last week did have a lot of internal customization. And that was one of the limitations that really kind of stumped us this week, was that lack of customization and transparency almost in the code.
But yeah, there is also source codes available, and I have tried changing the loss functions, but that can be done, but it comes with a lot of getting inside the code and trying to see what they have done because we didn't write the code.
Yes. Okay, great. Great job. Okay, thank you all for your participation. Our group done great. So we rate each team based on their performance, their research, the way they conduct the project and all in the afternoon. And please come back at 2 p.m. with our celebration and closing of WaterSoftHack program. So all videos are available again on our YouTube channel, the presentations as well as the position papers and slide would be available on our website. Please check our website if you're interested to learn more about the project. And again, I thank each group for their contributions. So I see you all at 2 p.m. with the celebration session. Thank you.